Alright, welcome back to Educator.com. Today we're going to talk about variables, equations, and algebra. What is a variable? We talk about them all the time, so we want to think of a variable as just being a placeholder. It's a placeholder for a number. It's a symbol that stands in for something that can come in later. It's standing in for a number. Sometimes the variable will be able to vary. It's going to be able to change depending on what we want to do. And as the value of the variable changes, it will affect something else. It might affect the output of a function. It might affect some other dependent variable. If we see something like y equals 3x, where we change x, we make it the independent variable, so we put in different things for x, and it causes our dependent variable y to change, varying on what we put in for x, or something else. So that's one way of looking at a variable. It's something that's allowed to vary, and it causes other things to shift around as it changes. Other times, we're just using a variable as a fixed value we don't know yet. Sometimes it might even be multiple possible fixed values, so it could be fixed values or fixed value, but the point is it's something that we just don't know yet. So it's a placeholder for something that we want to find out more about. So normally we're going to be able to figure out what it is based on the information given to us in the problem. Otherwise, it's probably not going to be a very good problem if we can't actually solve for what the variable is. So we'll almost always have enough information to figure out what is this variable. So that's the other possibility. A variable is something that we just don't know yet. It's a number that's been given a name because we're trying to figure out more information about it. It's like, if a detective is trying to find out who committed a crime, they might talk about the perpetrator and they might find facts out about the perpetrator until they have enough information to be able to figure out who the perpetrator actually is. Perpetrator is just a placeholder for some other person until they figure out who that person is. Great. We can name variables any symbol that we want. Normally we're going to use lowercase letters to denote variables, but occasionally we will use Greek letters or other symbols. When we're working on word problems, we want to choose our symbols. We want to choose what letter or maybe other symbol that we use based on something that helps us remember what is it representing in this word problem. What am I using this variable to get across? There are a lot of them that we regularly use, and so we'll get an idea of what they are. Here we go. So any symbol could potentially be used for any meaning at all. We could make a smiley face, and I sometimes do use smiley face to represent a number, but smiley face is a little bit harder to draw than X, so we tend to use letters that we're used to drawing. Anything could potentially be used for anything else, but here's a list of common symbols used and what the meaning we normally associate with them is. Occasionally we'll have different meanings associated with them depending on the problem. We might use Y to talk about the number of yaks that there are at a farm, but generally we're going to use them as we see right here. All of this stuff right here. So X is our most common one, probably our favorite variable of all. We use it for general use when we're talking about horizontal location or distance. Y is vertical location or distance. T normally stands in for time. N stands in for a quantity of some stuff. Theta, this is a Greek letter. Theta. When we encounter Greek letters, I'll talk about them a little bit more, but mainly it's just going to be theta. We draw theta by hand. You just make something sort of like you're drawing a 0 or an O, and then you just draw a line straight across the middle of it. That's theta. R is radius. A with a capital A is area, capital V is volume, and we often use A, B, C, and K to represent fixed unchanging values, values that aren't going to vary and change into other things, things where we know that they are going to just stay the same, but we don't know what they are yet, or we might decide on what they are later on. Anyway, this gives us a general idea of what the normal sort of stable of variables we constantly encounter are. Now, you might use X for something totally different than what we've got here. You might use R for something totally different. You aren't stuck to just using this, but we're going to see them in a lot of problems, and we want what we do to make sense to other people, so it's good to sort of go along with these conventions for the most part. All right. What is a constant? A constant is a fixed, unchanging number. It is a value that does not turn into another value. So we can have variables become different values, right? We might plug in x is 3, and then plug in x is 5, and then plug in x is 7. But a constant only has one thing. It just stays the same. So anytime we see a number like 3 or 5.7 or negative 82 or anything that's just a number, It's a constant, because numbers don't change, right? After all, we don't have to worry about 3 suddenly turning into 4. It's just 3. It's going to be 3 today, it's going to be 3 tomorrow, it's going to be 3 forever, right? 3 doesn't suddenly jump around and become a new number. Occasionally, we might refer to a symbol that's representing a number as a constant. So we might say A is a constant in this problem. We might not know what value that symbol represents, but we know it can't change. So a constant is something that can't change. And other times, we might even refer to a symbol as a variable and just know that that variable is fixed, that it is a constant variable. Seems kind of like a contradiction in terms, but remember we're using variable more for the idea of placeholder. And while sometimes it varies, sometimes it can also just be a placeholder in general. A constant is something that isn't going to move around. It's one number and one number only. Doesn't matter if it's a symbol or if it's actually a number, but the idea is that it's something that's not going to change on us. A coefficient is a multiplicative factor on a variable. So anything that has some number multiplying in front of it and is a variable, like 3 times x, its coefficient is 3. So normally it's just going to wind up being a number, but occasionally it's also going to involve other variables. So not all coefficients are constants, not all constants are coefficients. For example, if we have n times x plus 7, we've got n is the coefficient of x because it's multiplied against x. But 7 is not a coefficient because it's not multiplying against any variables. 7 is a constant, though, because it's just a fixed number. So n is a coefficient, but it might not be a constant. It might be allowed to vary, but it isn't going to be. So n is probably not a constant, but it is definitely a coefficient. And 7 is not a coefficient, but it's definitely a constant. And we could even look at x as being a coefficient on n, right? We can look at it from n's point of view or look at it from x's point of view. So coefficient is multiplicative factor, constant, just something that doesn't change. An expression is a string of mathematical symbols that makes sense. So what do I mean by make sense? Well, you could put together a string of words in English that makes no sense, right? Like tree, sound, running, carpet. That didn't make any sense, right? Tree, sound, running, carpet. That was meaningless, but it was a bunch of words. So to be an expression in math means that you have to make sense. To be an expression in English, passing this idea along as a metaphor, would mean that it has to make sense as a sentence. So a string of mathematical symbols that make sense together, right? So 2 times 3 minus 5 could be an expression, but parenthesis, 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 times, divide, minus 4 times, plus parenthesis, that doesn't make any sense, right? That's just a bunch of things that have been put down on paper, right? They've just been written down, but they don't actually mean anything. So an expression has to make sense. That's one of the basic ideas behind it. Often we will need to simplify an expression by converting it into something that has the exact same value, but is easier to understand, and often is just shorter. For example, we might simplify 7 plus 1 plus 2 into the equivalent 10, right? 7 plus 1, 8, 8 plus 2, 10. So 7 plus 1 plus 2 has the same value as 10. They're both different expressions. They're different expressions, but they have the same value, so we can convert one to the other. We can simplify it if we want to. An equation is a statement that two expressions have the same value. We show it with an equals sign. So what's on the left side of the equal sign and what's on the right side of the equal sign, we know that those two things are the same. They have the same value. Each side of the equation might look very different, right? 3x plus 82 looks very different than 110 divided by 2, but that equal sign is telling us what's on the left is the same as what's on the right. It guarantees equality between the two sides. Algebra, for being able to do algebra, we need to have some sort of relationship between two or more expressions. In this course, our relationship is almost always going to wind up being equality. It's going to be based on having an equal sign between two expressions. The two expressions will be equal to each other, and that gives us an equation to work with, allows us to do algebra, do some stuff. We could potentially have a relationship that is not based on equality. We could have an inequality, where one side is less than another side, or one side is greater than another side, or we could have a relationship that is different than either of those. But for this course, we're almost going to entirely see equality, and that's going to make up pretty much all of the relationships we ever see in math will be based around knowing equality between two things. So the two expressions will be equal to each other, and this gives us a starting point to work from. The key idea behind math, not behind all math, but behind algebra, is simple, it's intuitive, and it is incredibly important. If two things are the same, equal, then we can do the exact same operation to both things, and the results will have to be the same. So let's look at it like this. If we've got a caret here, and then we have another caret that is exactly like that first caret, so they are a perfect copy of one another. So we have two carets. And then we come along and we pick up a knife. And we cut up this caret with the knife. And we cut up this caret with the same knife, exact same knife being used on both of them. And we cut up both of the carets in the exact same way, right? We cut 1-inch sections exactly the same on both of them. We're going to wind up having chopped carets from the first caret and from the second caret. But we know, because we did the exact same way of cutting them up, and we started with the exact same caret, our chopped caret piles will be exactly equal to one another. Since we start with the same caret, and then we do the exact same kind of thing to both of the carets, we will wind up having the exact same pile of chopped caret at the end. Now compare that to if we had a third caret. That was exactly the same as his other two caret brothers. But instead of instead of using a knife on him, we decide to shove him into a blender, right? We put him in a blender and we run it for a minute. Out of that blender, we are going to get a pile of carrot mush, right? We're going to have a carrot mush pile. And that carrot mush pile is going to be nothing like those chopped carrots. So it doesn't matter that we just started with equality. We also have to do the same thing. Starting with equality is important, but if we don't do the same thing to both objects, we don't do the same thing to both sides of our equation, we wind up with totally different things. We no longer have that relationship of equality that we really want to be operating on. If you shove the carrot into a blender, you're going to have something totally different than if you had chopped it up, right? If we do the exact same chopping to the carrot, we wind up getting the two carrots, we wind up getting the same pile of carrots. But if we do a totally different thing, like shove it into a blender, we've got something totally different at the end, right? We've got this pile of carrot mush, and it's nothing like what we've got from the other two. So the idea here is we have to have the same operation be applied to both. Doing algebra is based around this idea of doing the same thing to both sides. Now, of course, you've seen this idea before, but it's absolutely critical to remember. You have to remember this fact. Always do the exact same thing to both sides. If you don't do the exact same thing to both sides, you're not doing algebra anymore. You're just making fantasies up, right? You have to do the same thing. If you add 7 to one side, you have to add 7 to the right side. If you square the left side, you have to square the right side. If you say hoogledy-piggledy to the left side, you have to say hoogledy-piggledy to the right side. A huge quantity of mistakes that students make are because they forgot to do the operation on both sides. They used it only on one side, or they used slightly different operations on the two sides. If you wind up doing this, you're going to wind up making mistakes. Don't let this happen to you. Pay close attention when you're doing algebra. Make sure you're doing the exact same thing to both sides. You have to follow all the rules on both sides. Otherwise, we're just making stuff up. We're no longer following algebra. When you're asked to solve an equation, you're being asked to solve for something. This usually means solving the equation for whatever variable is in it. If more than one variable is present, you'll be told which variable to solve for. What does solving an equation mean? It means you're looking for the things that make the equation true, right? You are told that this side equals this side, right? Stuff on left equals stuff on right. But they've both got variables in it, or one side has variables in it, or one side has just one variable in it. But the point is that depending on what that variable is, or depending on what those variables are, that equation might no longer be true. So what you need to do is you need to make sure that this is true. You were told that it equals one another. So you have to figure out what variable, what value for my variable, or what values for my variables will make this equation continue to be true. I was told it was true from the beginning, so I have to make sure that it stays true. Most often you'll be able to figure out what the values are that make something true by isolating a variable or variables on one side. You'll isolate the variable on one side, and then whatever's on the other side must be the value of that variable. How are you going to do that in general? Normally you're going to isolate the variable by doing algebra. You will ask yourself, what operation would help get this variable alone? What would I have to do to this side to be able to get this variable on its own? Then you do that operation to both sides. You continue to apply these operations, asking yourself one time after another, what could I do to get this variable alone? You keep asking yourself, what could I do? You keep doing operations to both sides. And then you keep doing this until eventually the variable is alone on one side and you've solved it. You'll get something of the form like x equals blah, 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 blah of numbers, right? So you'll know that x is equal to this stuff right here. You'll solved it. Now, keep in mind, sometimes you won't solve something by directly doing algebra. Algebra will probably be involved, but you might actually be doing something a little bit more creative. For example, we'll see stuff like this when we work on polynomials. We'll see cases where we aren't just doing algebra, we're also trying to figure out some other stuff and think on a slightly higher level. But the key idea is we're figuring out what makes this equation true. What are all the possible ways to make this equation be true? That's the real heart behind solving an equation. It just so happens that it's very often a good way to solve it by doing algebra and getting the variable alone, because once you get the variable alone and on one side, that tells you what value would make that original equation true. Great. Order of operations. It's critical to remember the order of operations. We've known about this for a long time, but it still matters today, and it's going to matter for as long as you're doing math. Certain operations take precedence over others. In order, it goes parentheses, things in parentheses go first, then exponents and roots, multiplication and division, addition and subtraction. Always pay attention to the order of operations. If you forget to do the order of operations and you do it in a different order, disaster will befall your arithmetic. So always make sure you're working based on this idea of the order of operations. Also, I just want to point out something. Exponents and roots are two sides of the same coin, right? X squared reverses square root. Right? X squared root x, if you take something and you square it and then you take its square root, they reverse one another. Multiplication and division, they reverse one another, right? If we multiply by 3 and then divide by 3, it reverses. Addition and subtraction, they reverse one another, right? If we add by 5 and then we subtract by 5, they reverse one another. So exponents and roots, the reason why they go at the same time is because they're really two sides of the same coin. They have some similar idea going on behind them. We'll talk about that more when we get into exponents more later in the course. Multiplication and division, they do go together at the same time because they're two sides of the same coin, right? They can reverse one another. Addition and subtraction, they go together at the same time because they are working together. They are, once again, things that can reverse one another. So that's why we've got these things paired together. But parentheses, exponents, roots, multiplication, division, addition, subtraction. Always make sure you're working in that order, or at least whatever you're doing goes along with that order. Sometimes you might be able to do things where you don't have to follow this order absolutely precisely, because you might see something like 3 times 2 plus quantity 7 minus 5. Well, because there's this plus sign in the middle, we know that we can actually do what's on the left side and what's on the right side simultaneously, because they'll never talk to each other until both of the order of operations have completely gone through on their two sides. So we can just skip right to 6 plus 2 equals 8. We don't have to do everything there. But if you're not quite sure, if you aren't really capable with the order of operations, you can see this sort of stuff right off the bat, always go with the order of operations very carefully, very explicitly. Worst case, it'll just take a little bit longer, but at least you won't make a mistake. Distributive property. We don't want to forget about the distributive property. It allows multiplication to act over addition when it's inside of parentheses. So if we have 3 times the quantity, 5 plus k plus 7, end quantity, then that's equal to 3 times the first guy, right? Plus 3 times the second guy, k, plus 3 times the second guy, 7. So 3 times 5 plus 3 times k plus 3 times 7. That's the distributive property. Always make sure you distribute to all the terms that are inside the parentheses, right? We have to distribute to everything inside of the parentheses. I see lots of students see something like this and they go, oh, 3 times 5 plus k plus 7. No. You have to do everything inside of the parentheses. Otherwise, you're not distributing. So make sure that you're always distributing to everything in there, everything when you're multiplying in there. All right. We can also use the distributive property in reverse, so to speak. We can go backwards in a way. This idea is what allows us to combine like terms. For example, if we have 3x squared plus 7x squared minus 5x squared, well, we got x squared here, x squared here, x squared here. So we can just pick them all up And we can shove them in because they're all multiplying, right? So we pick them all up, and it's times x squared. So we've got 3 plus 7 minus 5 times x squared. Because if we did the distributive property again, we'd get what we started with, so it must be the same thing. Now, 3 plus 7 minus 5, well, that just comes out to be 5, right? 3 plus 7, 10, minus 5, 5. We get 5x squared, and that's what we're using to allow us to combine like terms. We're sort of pulling out the like term, doing the things, and then putting it back in. At this point, we've gotten so used to doing it, we don't have to explicitly do this, but for some problems, it will actually wind up being a really useful thing to notice, so it's important to see that we can occasionally use the distributive property in reverse. Sometimes it will help us see what's going on. Substitution. This is a really important idea in math. We can use information from one equation in another equation through substitution. If we know that two things are equal to each other, we can substitute one for the other. For example, if we know that x is equal to 2z plus 3, and we also have this equation that 5y equals x minus 2, well, we can go, oh, hey, look, right here, I've got an x, and I also know that x is the same thing as saying 2z plus 3. So we take this information and we plug it in for x. So that's what gets us quantity 2z plus 3. We'll replace that x. So we have 5y is also equal to quantity 2z plus 3 minus 2. When we substitute, we need to treat the replacement the exact same way we treated what was initially there. So exact same way we treated what was initially there. The best way to do this is by putting your substitution in parentheses. Notice how I took 2z plus 3 and I put it in parentheses up here, even though right here, it didn't start off in parentheses. That's because I was substituting in for x, so I want to make sure 2z plus 3 is treated the exact same way that x was treated, so I have to put it in parentheses to make sure that it gets treated the exact same way that x got done. The best way to do this is always to just put your substitution in parentheses. It won't always be necessary. For example, on that 5y equals 2z plus 3, we didn't actually have to put it in parentheses there, but it will never cause us to make a mistake. It's never going to hurt us, right? Quantity 2z plus 3 is just the same thing as 2z plus 3 in this case right up here. And in other cases, like this one that we're about to talk about, it's absolutely necessary, otherwise we'll make bad mistakes, right? Consider this really common mistake. If we know that a is equal to b plus 2, and we know that c is equal to a squared, then we can go, oh, hey, a right here, I'll take b plus 2, and I'll substitute it in for a. Lots of students will go, oh, well, it's a squared, so it must be b squared plus 2. No, that's not the same thing, right? We need a to be all of what it is. A is all of b plus 2, not just the b part, right? And c is similarly not going to be equal to b plus 2 squared, right? This right here, not working because it has to be over this and this. Both, everything needs to get put together. B squared, not going to work here as well. The thing that we have to do is we have to have it in parentheses. The parentheses cause us to treat that a the same way that we are going to treat b plus 2. A squared, since a is equal to b plus 2, all of a has to be squared. All of that b plus 2 has to be squared. And the way that we get all of it is by putting it in parentheses. So whenever you're substituting it in, whenever you're substituting something in, make sure that whatever is getting substituted in, that it gets plugged inside of parentheses. Otherwise, lots of bad mistakes can happen. Sometimes, when you see the problem, you'll be able to go, oh, I don't actually have to plug it in parentheses, at which point, yeah, you might be right. Sometimes it'll make it a little bit faster, but really, it's a possible risk that you're taking for just putting down parenthesis. Not that much effort to put down parentheses, and it's going to save your bacon so many times. So I really recommend put all your substitutions, anytime you're substituting something in parentheses. Great. Let's do some examples. So if we want to simplify the following, 2 times 3 squared plus 4 times quantity, which is inside of that quantity 5 plus 7, and quantity times 2 minus 27. Well, we've got parentheses inside of parentheses. So first we go, let's work on the thing inside of the parentheses. And then inside of that, oh, we've got even more parentheses. So first we go 5 plus 7. We bring everything down, right? Each new horizontal line is a copy of what was above it, but just put in new ways of talking about it. 4 times quantity, well, what's 5 plus 7 become? 5 plus 7 becomes 12. So 12 times 2 minus 27. Now, we keep doing this inside of this parentheses first. 2 times 3 squared plus 4. 12 times 2 becomes 24 minus 27. 2 times 3 squared, still working inside of these parentheses. 24 minus 27 becomes negative 3. Now we've got 4 times negative 3, so now there's no longer anything to happen inside the parentheses. So what's next on the order of operations? Parentheses, then exponents and roots. So 2 times 3 squared, 3 squared is 9, plus 4 times quantity, negative 3. Next we've got multiplication, so multiplication, 18, plus 4 times negative 3, negative 12. Finally, we're down to addition and subtraction. 18 plus negative 12 becomes 6. Our answer is 6. One thing I would like to point out is if we're really good at math, we might have been able to go, oh, hey, look, there's a plus sign between these two sides. So these two sides aren't going to be able to talk to each other until they've done everything they have to do on their own two sides. So we could have hopped right down to saying, hey, 2 times 3 squared, that's the same thing as 2 times 9, which is the same thing as 18. And then we would have kept doing our stuff on the right side, but we could have been simultaneously doing everything on the left side because they're not able to talk to each other because they've got plus signs between them and everything else. That's a sort of a more advanced trick, and you're probably at the point where you can start seeing this sort of stuff. But if you have difficulty with the order of operations, you wind up making mistakes like this sometimes, be careful, go through it really carefully, make sure you've got that stuff completely underneath you. You need that foundation before math's going to be able to work. It's the grammar of math. It's like knowing the grammar of English. If you don't put words in the right order, it's just nonsense. If you don't follow the operations in the right order, it's just nonsense. We're not able to speak the same language as everyone else is speaking in math and what everyone else is expecting us to be able to do when we're working on problems or solving things or engineering bridges, whatever we're going to do with math. All right. Example 2, we use the distributive property to simplify. 5 times quantity x plus x squared plus 3 times quantity x plus y minus 7 times quantity x squared plus x plus y. So 5 times x plus x squared becomes 5x plus 5x squared. Plus 3 times quantity x plus y becomes plus 3 times x plus 3 times y. Minus 7, here's something we have to be careful about. It's not just going to be minus 7x squared, but minus 7 is the entire thing, right? So it's that minus 7 that gets distributed. So it's easier to see this as plus and then a negative 7. So plus negative 7, so negative 7x squared, plus negative 7x plus negative 7y. We have to make sure we distribute that negative as well. We see a minus, but it means that the negativeness has to be distributed to everything inside of there. Now at this point, so we can see things a little bit more easily, let's move stuff together. So 5x squared. And here's a little trick. If you're not sure, we've got like 1, 2, 3, 4, 5, 6, 7 different terms here, right? Lots of different terms here to have to work with. We can go, oh, hey, let's mark off each one. So we'll make a little tick mark after we write it on the next line so we don't get confused, accidentally use the same thing twice, or not even use it once. So 5x squared plus, what's another thing involving x squared? Minus 7x squared. So minus 7x squared. Plus, what comes next? Looks like we can work on the x's next. So 5x, tick there, plus 3x, tick there, plus minus 7x, plus negative 7x. And then finally, we've got the y's, plus 3y, plus negative 7y. So those tick marks just help us keep track of what we're doing. They're not necessary, but it makes it easier to follow so we don't accidentally make any mistakes. 5x squared plus negative 7x squared, those will combine to become negative 2x squared. 5x plus 3x plus negative 7x, so we've got 8x minus 7x. We've got 1x, which we just write as x, and 3y plus negative 7y becomes minus 4y. Negative 4y, which you can also just write as minus 4y. And there's our answer. Third example, we want to solve for x. So the first thing we do is we ask ourselves, how can I get x by its lonesome? How can I get it isolated on one side where it's just the variable and only one of the variable and nobody else there? So we go, well, it's inside of a fraction, right? Inside of a fraction, we want it to be on top, right? And we want it to be the only guy there. So we're going to have to somehow crack this fraction. How do we crack a fraction? We'll multiply by x plus 3, and that will destroy the denominator. Great. But if we multiply by x plus 3, then this 2 is going to get hit, and this 3 is going to get hit by the x plus 3, right? We have to hit everything, both sides. So the 3 will get hit by x plus 3, the fraction will get hit by x plus 3, and the 2 will get hit by x plus 3. So the first thing we want to do is we want to have some way of being able to have it operate on less things. So let's try to get it to operate just on the fraction, at least on one side. So what we'll do is we'll start off by subtracting 2 from both sides. That will make it easier to have sort of a clean shot for that x plus 3. We won't have anything else getting in the way. So that gets us 1 equals 5 over x plus 3. Now we can multiply by x plus 3, and well, we'll still have to multiply the 1. We have to multiply both sides, right? But we'll have at least a little less stuff in the way. So we multiply by x plus 3 over here, and we multiply by x plus 3 over here. So x plus 3 times x plus 3 on the bottom, they cancel each other out. X plus 3 times 1, that's just going to become x plus 3. Since we cancel out the x plus 3 on the bottom, we've got 5 here. Now we ask ourselves, how can I get that x alone? Oh, it's not too hard from here. We just subtract 3 from both sides, minus 3, we get x equals 2, and there's our answer. Great. Example 4, final example. This one's a little bit tough, but we can totally understand what's going on here. X equals 2z, y equals z plus 4. We want to solve for a in terms of z. So we've got a in this equation down here, and we've got x squared, and we've got y, and we've got x. So z doesn't currently show up in this equation. We want to solve for a in terms of z. So what that means is we want to get a equals blah, 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 with z's. Z's are going to be inside of that stuff on the right side, and we're going to have a by its lonesome. That's what solve for a in terms of z means. A equals stuff involving z, maybe multiple z's, maybe just one z, but it's going to be a equals stuff involving z. But notice it's not going to involve x, it's not going to involve y. We were told to solve in terms of z, so it's going to be only in terms of z and other actual numbers, that is constant numbers. So if we know x equals 2z and y equals z plus 4, we need to get that z stuff to show up here, and we need to get rid of the y and get rid of the x. So we'll use substitution. So x equals 2z and y equals z plus 4. So right here we've got a y, here we've got an x, here we've got an x. So let's do substitution. We've got the left side will still be the same, 2a minus 26 equals. What slots in for x? 2z slots in. So 2z in quantity, in parentheses, squared, plus 4 minus 2 times quantity, 3. What goes inside of y? Quantity z plus 4, close quantity, minus what goes inside of x? Quantity 2z, close up that. What we've got is our original, our sort of bottom equation, but we've now gotten rid of x, gotten rid of y, and we've only got z's and a's in here. Now we're able to solve for a in terms of z. So let's simplify what we've got on the right side, right? 2a minus 26 equals, we've got this plus sign in the middle, so we can work what's on the left and work what's on the right simultaneously. We don't have to worry about them interfering through each other, even though they don't show up at the same time in the order of operations. The only time they'll be able to talk to each other is when we get all the way down to plus, so we can have stuff on the left and stuff on the right work simultaneously to make it a little bit faster. So 2z squared, quantity 2d squared, we square the 2, we square the z. So 2 squared and z squared. Plus 4 minus 2, we go inside 3 times z plus 3 times 4 minus 2z. 2a minus 26 equals square 2. We get 4 square z. We don't know what z is, so it just stays as z squared. Plus 4 minus 2 times quantity, 3z plus 12 now, minus 2z. Keep simplifying. 2a minus 26 equals 4z squared plus 4 minus 2 times 3z minus 2z becomes just 1z plus 12. We can now distribute this minus 2. 2a minus 26 equals 4z squared plus 4. We distribute the minus 2, so remember it's plus a negative 2. So we get plus negative 2z plus negative 24. Now we're in a position to be able to keep simplifying the right side to its most fundamental level, equals 4z squared. We don't have any other z squared, so it's just 4z squared, plus 4, well, let's put our constants at the very end. So we'll go to plus negative 2z, so minus 2z, and 4 plus negative 24 becomes minus 20. At this point, we can now do our algebra. We'll add 26 to both sides, and we'll get 2a equals 4z squared minus 2z plus 26, so plus 6. Oh, whoops. I accidentally wrote what I was saying. So minus 2z still, add 26, negative 20 plus 26 becomes just 6. Divide both sides by 2, a equals 4z squared minus 2z plus 6 all over 2. And we can simplify that. 4z squared, that becomes 2z squared. Minus 2z, that becomes minus z. Plus 6, that becomes plus 3. So it's a equals 2z squared minus z plus 3. A equals stuff just involving z. We've solved for a in terms of z. Great. I really want to point out the reason we were able to get that right is because we put parentheses when we substituted in. If we hadn't done that, we wouldn't have had our square go on to both the 2 and the z. We wouldn't have our 3 distribute to both the z and the plus 4. We wouldn't have our subtract go, well, our subtract actually would have still subtracted 2z. But if we didn't put in those parentheses, we would have definitely made some mistakes. It's absolutely critical to put in parentheses when we're substituting. Otherwise, mistakes will just start popping up everywhere. All right. Hope all that made sense. We'll see you at Educator.com later. Bye.